record. Okay, so this will be the first of probably two lectures about inequalities. So this time we'll cover AMGM and Muirhead, and next time we'll cover Cauchy, Schwarz, and Holder. Um, yeah. So let's get started. Right, wait, so you guys were able to, you guys understood how to do problem two, like this problem. I gave a bunch of inequalities. You guys were able to solve them. Yeah.
Yeah.
Okay. And so you understand the point, right? You basically have to pick the weights, so make everything work, right?
Yeah.
Okay. All right. So okay. So right. Maybe that's point. Okay. What about problem three? Were you guys able to solve this one? So maybe let me just write it down. So it's uh okay, so the condition is let's assume A plus B plus no, sorry, A plus 2B plus 3C equals 6. What is the maximum value? Okay, all are positive. Of A, B squared, C cubed, right? So, okay, yeah, so this is a direct application of um, AMGM, like we have sixth root of A, B squared, C cubed, right? Okay. Um, do you guys understand how to do it? If I say 3A plus 2B plus C equals 6, then what is the maximum value of A cubed B squared C?
Yes.
Okay. Yeah, okay. So maybe someone can explain it to me. I don't know. Are all three of you, do all three of you understand how to do this? Adham, you understand how to do this? Or Abdullah, you guys understand how to do this?
Yeah.
Okay. Yeah, okay. Um, yeah, okay, maybe I can just, so yeah, what are the weights? I say, uh, okay, it's actually it's the same. It's 3A. No, let's wait. How does it work? So I write, um, so I do weighted AMGM. So on the right-hand side, I want to have, um, A to the 1/6, B to the 2/3, sorry, B to the 2/6, and C to the 3/6. So I write 1/6 times okay, something A plus 2/6 times something B plus 3/6 times something C. Okay, and then I want to pick the weights so that I get 3, 2, and 1, right? So maybe do 9, 4, and 1, is that right? No, is this? Okay. Can you guys tell me what the weights are? I forgot. So yeah, I'm asking what are the how do I finish the solution? Um,
We know that the left hand
the left hand side is equal to 1, so we can just um,
No,
multiply.
no, it's the left hand side is not equal to 1 because I've changed the condition, right? I need to put here the correct numbers.
Um,
Did you see the point? It's not the condition is different, right? If I just apply like the left hand side is not equal to 1 unless I put some kind of weights here. Did you guys see the problem? Okay, sorry, why did I write a cubed b? I meant here a b squared c cubed. Okay, like this. Right, so the condition is that 3a plus 2b plus c is fixed, and we want to maximize a b squared c cubed. Does it make sense what
yeah.
but it's you can't directly apply AMGM. You have to do something clever first, right? So what's the like how do I apply AMGM now? If I directly apply it, then okay, on the right hand side I get the right thing, but on the left hand side I have the wrong thing, right? Do you guys see the fix?
Yeah.
So how do I fix it?
Um, we can put 3a and b can just be 1 and c can be 1 over 3.
If you put 1/3, now what happens now? So now we get what? Now it's okay. Now it becomes 3a here. B stays the same, and this one becomes 1/3c. Well, now what? So now on the left-hand side, we have uh, but it becomes 1/2 A plus 1/3 B plus 1/6 C is greater than or equal to what? What we want times some factor, right? 3 to the 1/6 times over 3 to the 1/3, which is 1/3 to the 1/6. Okay, maybe we can just 3 to the negative 1/6, right? Because we have like this. Okay, and so then what this side is equal to 1. And so we get what we get the maximum value is 3 to the 1/6, the sixth, so it's 3. Okay, but 3. Yeah, okay, so it makes sense. It's okay. Karam, I know you just joined, but do you have any questions about this problem? Okay, maybe let's move on. So, okay, maybe let's then talk about the. Well, actually, okay, let's talk about Muirhead. Okay, so I'll come back to the other one. So, you guys know the statement of Muirhead's inequality?
Which
It's
one?
Muirhead's inequality. So let me
Oh,
state it right now. Okay, yeah, so this one is right. So Muirhead's. Okay, maybe actually before we go to Muirhead, let me just go through these. So the point here is, okay, when we look at these inequalities, right? So the point is like, okay, okay, for each of these inequalities, what's happening? You have a symmetric, you're comparing two symmetric polynomials, right? And they're equal when A, B, C are one. Like they're basically they're symmetric polynomials that have the same number of terms. And so when can you say one is stronger than the other? The point is like, okay, ABC is very weak because it has like the powers are evenly distributed, and A cubed is very strong because the powers are very unevenly distributed. So, okay, Muirhead is some general way of comparing these. So let me just write it down. Okay, so what you need to understand is something called majorization. Okay, so actually, let me ask. Okay, how many of you guys know what the majorization means? Like, how many of you guys know the statement of Muirhead's inequality?
on a
I don't.
sequence.
So maybe I think we should go over it. Okay, yeah, okay. So the point is this. So let's look at, I think this is a good example, this one here, right? So so the one here, let's look at these inequalities here. So we have a to the fifth plus b to the fifth plus c to the fifth is greater than or equal to a cubed bc plus ab cubed c plus abc cubed, and then abc ab plus bc plus ac. Okay. All of these are like symmetric, so they're all symmetric in ABC, and they're all degree 5. They're all homogeneous degree 5. Okay, and they have the let's see, same number of terms. So they all are 3 terms. Okay, so or we can say like yeah, they're all 3 terms. And we want to be able to compare them. So what all that really matters is the exponents here. So this one is a to the 5, b to the 0, c to the 0, right? So this is exponent 5, 0, 0. Yeah. Makes sense what I mean by exponent 5, 0, 0?
Yeah.
Okay, and then this is 3, 1, 1, and this is what is it? 2, 2, 1, right? Okay. So what I want to say is that this exponent here, 5, 0, 0, is stronger than 3, 1, 1, and 3, 1, 1 is stronger than 2, 2, 1. Okay. And the way we say that is we use this concept called majorization. So we have to give a definition. So if I have two sequences x1, x2, xn, and y1, okay, and y1, y2, yn. So these are the sequences of exponents. So all, let's say, greater than 0, maybe greater than or equal to 0, right? And they don't have to be integers actually, but okay, then we'll say x1, xn, this symbol, it means majorize if the following is true. So it means we need First of all, they should have the same sum. You can't compare them if they don't have the same sum. And then we say x1 is more than y1, more than or equal to, then x1 plus x2 is more than or equal to y1 plus y2, and so on. Yeah, like this. So like, and then next inequality is x1 plus x2 plus x3 is relative to y1 plus y2 plus y3, and so on. Yeah. So does it make sense what the definition of majorization is?
Yes. But how is it useful?
So the point now is, if I have, so what's the theorem? So this is called, the theorem is, yeah, let's say the theorem. Can I zoom out? Yes, I can zoom out. So the theorem now is that, yeah, so and this is Muirhead's inequality. If x1, x2, xn majorizes y1, y2, yn, then you have the following inequality. You can take a1 to the x1, a2 to the x2, an to the xn, but you have to make it symmetric. So you write this, and it's now greater than or equal to a1 to the y1, a2 to the y2, an to the yn. Of course, we should assume that all the variables are positive. Okay, so if all the variables are positive and the exponent of the left-hand side majorizes the exponent of the right-hand side, then you can compare them like this. Okay. So do you guys understand what I mean by symmetrics when I write this symbol, sim?
Yeah.
Okay, it means I now have to run over all the permutations. So let's do an application here. So let's apply it to the exponent 5, 0, 0 majorizes 3, 1, 1. Okay. So it means now I can say the symmetric sum of a to the fifth is greater than or equal to the symmetric sum. Where did I go? Okay, yes. It's greater than or equal to the symmetric sum of a cubed bc. Okay, but what does symmetric sum mean? So, okay, I have 3 variables, there are 6 permutations. Okay, so what are all the permutations? It's going to be like a to the 5, b to the 0, c to the 0, plus a to the 5, b to the 0. Like I have to, because there's like 2 zeros, I'm counting every term twice. So the left-hand side is going to be 2 times a to the 5 plus b to the 5 plus c to the 5. And the right-hand side will also be double. It'll be 2 times a cubed bc plus a b cubed c plus a b c cubed. Does it make sense? Why there's the factor of 2?
Yes.
But of course it cancels, but you need to keep it in mind because you don't want to write something like a to the 5th plus b to the 5th plus c to the 5th is greater than or equal to like I don't know, let's compare it to like, or okay, let's use it. Okay, so the reason you need to write symmetric sum and not is just, okay, you can say something like maybe I'll do it here. So let's say I know 3, 0, 0 majorizes 1, 1, 1, right? Okay. So, but no, I can't just write something like a cubed plus b cubed plus c cubed is greater than or equal to abc. It will be nonsense, right? Like they have a different number of terms, right? So if I take the symmetric sum, what it really says is, okay, now I have twice a cubed b cubed c cubed is greater than 6 abc. And that's the correct inequality, right? Like this is AMGM for 3 variables. Okay. So do you guys understand now the statement of Muirhead? So Please, because please stop me here because this is very important to understand inequality. Okay. Now, let's see, before we continue, let me say something. The way you should use Muirhead is you should not actually use it to prove. Well, okay, you can, but you should really use it to know when something is true and then use AMGM to prove it. So let me just, yes, let me say what I'm saying. So warnings about Muirhead. So for example, let's look at this list of inequalities that was one of the warm-ups. So let's look at the very last one here. Okay. A to the 7 plus b to the 7 plus c to the 7 is greater than or equal to a to the 4 b cubed plus b to the 4 c cubed plus c to the 4 a cubed. Okay, so we know 700 majorizes 430. Okay, but that doesn't prove this inequality. Why?
Because we end up with more terms on the right hand side than we need. We get a to the 4 c squared and so on.
That's right. So the right hand side, it will have, if we applied Muirhead, we would get a to the 7, b to the 7, c to the 7 times 2 would be greater than or equal to a4 b cubed, but we'd also get a to the 4 c cubed, right? You would get extra terms. So you
Because
can actually not use it.
because the one above is cyclic and not
That's right,
symmetric.
yes. Exactly right. So this is, should be careful, this is cyclic, not symmetric. That's the inference, right? So, but it doesn't mean we're done. It means we know we should believe that it's true because of Muirhead, and then we should prove it using AMGM. Okay. So what do we do with AMGM? Well, we say, okay, we want to prove what we'll say, okay. I think it goes something like 4/7 times a to the 7 plus 3/7 b to the 7, right? So yeah, is greater than or equal to a to the 7 4 times and b cubed. Oh, sorry, b to the 7 3 times, right? So and what is this? This is equal to exactly what we want, a to the 4 b cubed. And now we just sum this cyclically and we get what we want. Okay. So that's why you should think of Muirhead as some kind of philosophy for telling you when you can compare two sets of, like two polynomials, but it's not always a proof. Okay. Let me give some more examples of this Muirhead. So, yeah, okay, so, okay, one example, I give you this inequality here, a plus b plus c cubed greater than or equal to a. You should know immediately that it's true, right? Can you explain why it's true?
If we were to expand the left-hand side, we would get directly Muirhead. It follows directly. Because
Yeah,
we would
right, so
have...
yeah, go ahead. Well, we have to do one thing, right? We have to cancel
We
the
would
A cubed, B cubed,
divide,
C cubed.
yeah, we would divide, yeah, but then we would divide by 3 and it follows by
Yeah, that's right. Yeah, right. Because right. So we cancel the A cubed, B cubed, C cubed, and then all that's left is whatever terms are left. We actually don't have to calculate them. We know they're going to majorize ABC because ABC is the weakest term under majorization, right? So, Okay. Now let me mention this one here. So yeah. So a cubed over bc, b cubed over ca. Yeah. So
We add the terms on the left-hand side and then multiply by ABC. Then again, it follows when we.
you're saying I do this. You're saying if I add them, what happens?
We get a cubed
I-
plus b cubed over c cubed, and we multiply by ABC. So we get a cubed plus b cubed plus c cubed is bigger than or equal to a squared bc plus b squared ac plus c squared ab, which is the same as Murray because when you have powers of 1, it's just
it'll
the
be
same
it'll
as
be
multiplying by.
it'll be fourth, right? If I not cube the fourth, but is that right?
Oh, it's 4.
Yeah. But
Yeah,
you want
it should work. It still works.
yeah, it still works.
think.
It still works, right? It still works, of course, it still works. Yeah, still works.
Because you
Okay,
divide
great.
by 2 when you apply math.
Yeah, exactly right. Yeah. But I also just wanted to point out that you actually don't need to multiply by ABC because you can think what's going on here. It's not really that much of a difference, but okay, whatever. You can say that what I have is 3 minus 1 minus 1 compared to 1, 0, 0. Okay. So you can't apply Muirhead's theorem because the exponent is negative, but you can still apply the idea that there should be an AMGM proof. And indeed, there is an AMGM proof to this. So like without multiplying through, I can even say something like, okay, I have let's think. So if I do a cubed bc over bc, but I now square it. No, I cube it, I believe actually. I cube it. And then I do b cubed over ac once and c cubed over ab once. What happens now? So now what's left? This is a to the 9 over did I do too many? Maybe I wanted to square it.
We can apply more.
Apply what?
We can apply Muirhead from the start.
Does Muirhead work when the exponent is negative?
Yeah,
Okay.
measurization doesn't require them to be positive reals.
Okay. In that case, okay, you can apply. But I just wanted to explain, like, you can also write an AMGM proof, and I think maybe it's good to like know how to write the AMGM proof, right? So, like the AMGM proof from the beginning will be I want to basically create A here, right? So maybe if I write square, let's see. If I write square, I get A square.
Actually, I think there's a mistake in the inequality. We should have the term a squared bc, not a cube.
Yeah, it's a squared. But it still follows. It doesn't matter.
Oh, you mean here? Yes, you're right. You're right. Here there is yes. That's right. That's right. A squared. Yes, that's right. Yeah, of course, because they should be homogeneous. But great, yeah, thanks. So it should be like this. But I just wanted to make a point that you can directly from here like figure out the AMGM proof, right? Like the AMGM proof, even if you don't clear denominator, should be like this, right? Because if I write this, I get what? I get b squared and b, and so it all cancels, right? So and now I take to the power of 1/4, right? So now and this compares to on the left-hand side 1/2 of a cubed over bc plus 1/4 of b cubed over ac plus 1/4 of c cubed over ab. And what is this? This is equal to exactly a. And so then we're done because we just sum cyclically. Does it make sense? What does it make sense what the argument is from here? Like I have a. Do you guys understand why like what I wrote here? Like this follows from AMGM, and then this implies the first inequality directly. I don't know if you guys are following or not.
But why this implies the original inequality?
Because now I sum cyclically, right? So now I take like now what? So now I say I can say 1/4 times a cubed over bc plus 1/2 b cubed over ac plus 1/4 c cubed over ab is greater than or equal to b, right? And then I can do it for c. And do you see, like on the right hand side, I'll get a plus b plus c. Yeah,
Yeah.
it
So
makes
we,
sense.
yeah, at the end we will have 3/4 of the left hand side is greater than or equal to the right hand side.
Not 3/4. We'll have exactly the left hand side, because we'll have 1/2 plus
Yeah.
1/4 plus 1/4, right?
Yeah. Okay.
Makes sense.
Yes.
I mean, it's okay. It's not, we're not doing, anything much more than what we did before, but you should get into the habit of writing, like figuring how to figure out the weights in an AMGM proof, right? Because, okay, let me give an example, right? So, like, okay, you won't always be able to apply Muirhead directly, right? You have to know how to write the AMGM proof. So let me just give an example. So, okay, so let's look at okay, let's look at this example. Let's look at this problem here. Okay, you'll see the point I'm trying to make. So this is problem 8.
We start by applying AMGM over A4B plus ABC squared D plus ABCD squared, and we see that it's bigger than 3 multiplied by A squared BCD. However, on the left-hand side, we end up with 2 cyclic sums that are equal to the right-hand side. So after we subtract them, we end up with the equality.
Wait, actually, wait, let me first copy this problem. So yeah, maybe okay. Let me so okay. So the zoom is we have a, b, c, d greater than 0, and the product is 1. Okay, so we have a to the 4th b plus b to the 4th c plus c to the 4th a plus d to the 4th c to the 4th d plus d to the 4th a is greater than or equal to a plus b plus c plus d. That's what we want to show. Okay. And so, okay, what is the first thing you're suggesting, Adham?
We apply AMGM over A to the 4B plus ABC squared D C zone squared C squared D plus ABCD squared.
Okay,
This
over
is
3, I guess.
no, we can remove the 3 and just put the 3 on the other side.
Okay.
It's bigger than or equal than 3 or multiplied by the cube root of a to the 6 b cubed c cubed d cubed, which is just a squared bcd.
Okay, a to the 6th, 1, 2, 3, b cubed, b cubed, d cubed, right? Which is 3a squared bcd. Okay, now what?
Then we this statement is true when you add cyclic sums on both sides, and on the left hand side we see that the second and the third term are just the same as the left hand side cyclic sums. So we subtract them and end up with the exact inequality.
Okay, very good. That's very good. So okay, this works. It's very nice. So Right, and this is just equal to 3a. But let me try to explain how to come up with the solution. This is a very nice solution, but let's try to explain how does one come up with the solution, right? So the first thing you should do when you see this problem is you should realize that this is not a homogeneous inequality. Like the polynomial here is degree 5 and degree 1. Okay, so what we do is something called homogenization. So what we do is we take this inequality and we homogenize it. So we write it as e to the fourth b plus b to the fourth c plus c to the fourth d plus d to the fourth a. And now what we say is like this: a, b, c, d times a plus b plus c plus d. And so the point here was before it was the two sides were degree 5 and degree 1, but now they're both degree 5. And we didn't really do anything because we just used this condition a, b, c, d equals 1. So the point is now we can just have this inequality when we forget about the condition. Does it make sense? So does it make sense what I mean by homogenization?
Yeah.
Okay, but now, so now what? So now, okay, we can think about mirror heads. So what are the exponents? They're 4, 1, 0, 0, and on this side they're 2, 1, 1, 1. Okay, and so the left-hand side majorizes the right-hand side, but it's not symmetric. So we can't use mirror heads. So we have to figure out what the weights are. So how are we going to do this? We want to we want to do something like this. We want to do a to the fourth b to the power of some weight plus b to the fourth c to the power of some weight plus times c to the fourth d to the power of some weight and d to the fourth a to the power of some weight. And then here we'll have the weighted average. And what do you want? We want the right-hand side to basically end up being a squared bcd. Okay. But okay, now I'm actually a little bit worried. Okay, so yeah, so okay, so now the point is you need to figure out what these weights are, right? So that you get this. And the guarantee for mirror head is you will always be able to calculate the weights. So maybe I'll leave it as an exercise. Is that okay? Do you guys see how you would do it for me? Okay, I'm not sure if do you guys understand how this solves the problem? You can find these weights. I think maybe some people are confused. I'm not sure. Okay, let me ask. So, do you guys understand the technique that, do you guys understand the strategy that I'm using here? Maybe. Maybe let me explain a little bit more. So, the point is, okay, so the claim I'm making is there exists positive weights, W1 plus W2 plus W3, that up to 4, such that a to the fourth B to the W1, B to the fourth C, W2, C to the fourth D, W3, C to the fourth A, W4 equals A squared B C D. Okay. Does the claim make sense?
Yeah,
And do you understand? If the claim is true, why it solves the problem?
because we can just also do it cyclically.
Yeah, you just sum it cyclically, right? So the only thing is, like, why do you know these weights exist? And what I'm saying is, if you have this majorization thing, then you can always do this. This is basically what Mehrad guarantees you. Like, okay, what does it mean? We have to solve an equation, right? So it means you have to write 4W1 plus W4 equals 2, and then W1 plus 4W2 equals 1, and then from C we have W2 plus 4W3 equals 1, and then from D we have W3 plus 4W4 equals 1, right? And I claim the solution to this, the W1 to W4 will all be positive. This is what Mehrad guarantees. But you have to find them. Does it make sense what I'm saying?
Well, how can we find them?
Well, it's a system of equations. Yeah, you have to solve it. Like, this is a linear system of equations.
Ah, okay.
You see what I'm saying? Yeah. Like, you can just I can. The linear,
Yeah.
you can substitute. Yeah. Okay. So
Yeah,
you
we
have to
can
solve
solve.
this, but the solution will be weird. But you'll find the weights, and then you can prove the inequality. Yeah. So I'll leave it as homework. Okay. But the point is, you can all, like, the reason that you end up getting positive weights is because of this majorization condition. Otherwise, it wouldn't be true, right? So that's what the idea of Mehrad is. Like, anytime I have this condition, I can do an AMGM argument, but I might have to calculate what the weights are.
Okay.
Okay. Okay. Let's see. So okay, let me just now give some more examples of homogenization. So okay. Let's see. So let's do this first one here. So yeah, okay. ABC equals 1, then no, sorry, that's what I want. Sorry. ABC equal to 1, and then A plus 1, B plus 1, C plus 1 is greater than or equal to 8. Okay. So so this is another inequality which is not homogeneous because okay, so the right-hand side, this is degree 0, but the left-hand side is mixed degree. Yeah, the problem, it has term, it's like this, it's not really homogeneous, right? So one thing you can do when you see this inequalities, you can homogenize it.
We can also just expand it, and it would follow by applying AMGM twice.
Okay, we can expand it.
Yeah.
Let's see.
I think we can do it without expanding.
Okay, so there's three methods here. So so one is to expand,
Yeah,
one is without expanding, and the other one is homogeneous. So maybe we can look at all the solutions. So let's maybe start with, if I expanded, what happens? And I get
ABC plus A plus B plus C plus AB plus AC plus BC plus 1. We already know that we can just keep A plus B plus C by AMGM is bigger than or equal to 3, and AB plus AC plus BC is also bigger than or equal to 3 by AMGM. So it's just
great.
1 plus 1 plus 3 plus 3, which is bigger than 8.
Okay, great. So this is greater than or equal to
3.
3 greater than or equal to 3, and then this equals 1. Okay, and then we're done. Okay, so it directly follows from AMGM. Okay, great. So that's one solution. What about okay, now, Karan, what's your solution if I don't expand?
For the expression A plus 1, we apply the AMGM and we have A plus 1 is bigger than or equal to 2 square root of A, and the same thing for B plus 1 and C plus 1. Then we multiply all of them, so we have the left hand side is bigger than or equal to 8 times the square root of ABC, which is 8 times 1.
Great. Okay, great. Great. So now, great. So all of these are good solutions. I want to, yeah, so good. So these all work. I want to explain something that is actually a harder solution than both of these, but it's like, I don't know, it's like a brainless, like it doesn't require anything clever. Okay, okay, let me explain what I'm saying. So so these are all good solutions, but now there's a solution where you homogenize, and the point is it's not as clever, but it has to work. Okay, so let me explain what I mean. So okay, what's the big problem with this inequality is, okay, on the right hand side I have a degree 0 term. On the left hand side it's some kind of mixed degree. So I can homogenize everything using this condition. Okay, so what does it mean? I want to make, let's say I want to make, yeah, so the easiest way I think to homogenize is to make, maybe we can do it. We can say, we'll make all the degree 0 terms degree 1. So I'll make it like this. I'll say A plus ABC to the 1/3, B plus ABC to the 1/3, C plus ABC to the 1/3 is greater than or equal to 8 ABC to the 1/3. Okay, so now everything is degree 1. Does it make sense?
Shouldn't we make the right hand side just ABC? Because the left
yes,
hand side is, yeah.
Sorry, yes, ABC. Everything is degree, sorry, yeah, you're correct. So we should make everything degree 3, right? So now, okay, they're both, sorry, so it's my mistake, it's degree 3 on both sides. Okay, so yeah, so we made the constants that were degree 0, we made them degree 1. So now each factor is degree 1, so this whole thing is degree 3. And we want the right side to be degree 3, so we write it like this. Yeah. Yeah, does it make sense?
Yeah.
And now, okay, now it's actually like something, you can do it maybe, okay, when you expand, what happens? On the left-hand side, we'll have a bunch of terms, but we know they're all going to majorize ABC. And we know, okay, both will be 8 terms on the left-hand side, 8 terms on the right-hand side, right? So let's say what I mean. So like both sides are degree 3. both sides are 8 terms, and we know the left-hand side, like whatever terms show up, they're all stronger than ABC because they all majorize ABC, right? So then we can solve the problem using AMGM or something. Does it make sense?
Yes.
The point is, this solution is worse than the other two, but it's I don't know, it's the point is that it's robotic. It's not don't do anything. Okay, maybe I'll just give some other examples. So okay, let's think. Okay, so maybe let's look at this one. Yeah, okay, so I'm missing the problem. Okay, we can look at this one. So yeah, so the problem is this one. Let's so 1 over A, 1 over B, C. Okay, so we have A, B, C more than 0, and we have A plus B plus C equals 1. And we want to show that 1 over A plus 1 over B plus 1 over C is greater than or equal to or less than or equal to 3 plus this thing. Okay. A cubed plus B cubed plus C cubed over ABC. Okay. A cubed plus B cubed plus C cubed over ABC. Okay, so this is the inequality. So I'm going to have positive reals. Right, so we have the same thing again where the left-hand side is degree -1, and then this one is some kind of mixed degree, so it's degree 0, and then this is also degree 0. Okay, so it's degree -1 and degree 0. But we have a condition, right? So because we have a condition, because we have a condition, we can turn this inequality into something homogeneous. Yeah, so what's the easiest way to do this?
I think I did it in a really long way. I added the terms on the left-hand side first and multiplied by ABC. And after that, I multiplied the left-hand side once more by A plus B plus C. Then it just follows by Moriarty.
Okay, good. So there's an explicit solution where I collect all the terms. So there's an explicit solution where you multiply everything out. What I'm trying to explain is there's some kind of a systematic solution as well, right? So yeah, so by the way, do you guys understand what I mean when I say the two sides are degree -1 and degree 0? Does it make sense what I'm saying?
Yeah.
Okay. So right, so wait, so here's the first one. How do I turn this into something that's homogeneous where both sides have the same degree?
Maybe substitute 1 in the left-hand side with A plus B plus C.
Great. Yeah. So what we do is we can so you can think of it as, instead of writing 1, you write A plus B plus C. Or you can just think about it, I'm multiplying the left-hand side by A plus B plus C, right? I mean, it's the same thing, right? You can, instead of writing 1, you can write A plus B plus C, or you can just multiply the left-hand side by A plus B plus C, and it doesn't change anything, right? So we have A plus B plus C times 1 over A plus 1 over B plus 1 over C, and we have this. Okay. And now both sides are degree 0, right? And we can since both sides are degree 0, we can just drop the condition. So there's no condition now. There's no A plus B plus C equals 1. Okay, now before we proceed, let me ask something. Do you understand why these are equivalent? Like, if I have this inhomogeneous inequality with a condition, it's equivalent to the homogeneous version with no condition. Like, if you can prove one, you can show the other.
Yeah, because we used it.
Yeah, but okay. What that means is if this is true, then no, let me say. If this is true, that implies this. But what about the other direction?
How have we concluded that if the second inequality is true, then the first is true? We don't
Well,
know
if the
the condition in the second one. We don't know the condition is true.
right. So okay. Right. Let's okay. Yeah. Maybe I have to be a little bit clear. So let's call this statement 1. Yeah. So let's call this statement 1. And this one is statement 2. So if you know statement 2, that automatically implies statement 1. Right? Because, like, let's say I assume this, right? Then when I go to statement 1, I can just plug in A plus B plus C equals 1, and I get the result. Does it make sense? I think Karam, your question is how do I show that statement 1 implies statement 2? Maybe that's what the.
No, I mean how statement 1 implies statement 2. Statement 2 implies statement 1.
Oh, so which one are you asking? Why statement 2 implies statement 1, or why statement 1 implies statement 2?
Why statement 2 implies statement 1?
Okay, so statement 1 is that statement 1 is if I have A plus B plus C greater than 1, then this, right?
Yes.
So if I know statement 2, I know this inequality is true for all ABC that are greater than 0. Then if I further have A plus B plus C equals 1, then
so
we just substitute.
So statement 1 is an implication statement.
Yeah, statement 1 is an implication. Statement 1 is saying is if this, then this, right?
Yeah, I thought that statement 1 is the inequality without the condition.
No. Statement 1 is no. Statement 1 is the problem, right? So if this is true, then I have this, right? It's implication, yeah.
Yeah.
Yeah. Okay. So statement 2 implies statement 1 is clear. Statement 1 also implies statement 2, right? That's not as easy. If I know this, now I have any arbitrary ABC, I can scale them so their sum is 1, and that doesn't change either side. Does it make sense what I'm saying?
Yeah.
So like these are actually equivalent. So
yes.
So yeah, Karam, does it make sense?
But statement 1 implies statement 2. But why?
Yeah.
Because statement 1 is an implication. We don't have the
Yeah.
condition must be true.
Yeah. So it's yeah, but let's say I have statement 2. I have arbitrary ABC. And what I can do is I can turn A prime, B prime, C prime are basically A over A plus B plus C, B over A plus B plus C, and C over A plus B plus C. I just scale them so that their sum is 1. That won't change the value of either side because they're both, you see, they're both degree 0. Like what I'm saying. So the point is this: anytime I have a homogeneous inequality, let's say I want to prove A squared plus B squared greater than 2AB. The truth of this inequality doesn't change when I scale A and B by the same number.
Yes, because it's true for all numbers.
No. Let's say I didn't know that. Let's say I didn't know it's true for all numbers. You see? Let's say I don't know that yet. But whether this inequality is true, it doesn't change when I scale A and B by the same amount. Okay, maybe I
But
think
what?
I need to. Because if I scale, let's say I double both A and B, then both sides get multiplied by 4.
Yes, but
So I
A
can. Mhm.
and B are multiplied by the same factor.
By the same factor, right? And so I can always choose a factor so that their sum becomes, say, 1, for example. Uh, okay, I don't know if I'm.
Yes, so we multiplied both of them by some number k such that k plus kb is 1.
Yeah, exactly. Right. And do you see now why that shows that statement 1 or statement 2 follows from statement 1? Because if I want to show this inequality for arbitrary A, B, C, I just scale them by a number so that A, B, and C have sum 1. And then I apply
Yeah,
statement 1.
and that number should exist.
And that number should exist, right? So it makes sense now?
Yes,
Yeah. So, okay. It's a little, okay, it's kind of a long thing we were discussing, but the conclusion is anytime I have a inhomogeneous inequality with a condition, I can turn it into a homogeneous inequality, and they are equivalent to each other. So I can just solve the homogeneous version. Does it make sense?
yes,
So that's the idea of homogenization. Like I take an inhomogeneous inequality with a condition, it's equivalent to homogeneous inequality. That's the idea. Okay, so in this case, the homogeneous inequality I come up with is this. But how do we solve this?
I think we multiply the left hand side, then we subtract the 3 because we will have some ones. Then we can multiply by ABC.
We can multiply by ABC or yeah, so okay. Maybe we have what we'll have is twice A over B. Oh no, not twice. We will have A over B plus B over C plus C over A plus A over C plus
C over B.
C over yeah, C over B plus A over like this, right? No, what did I
Plus
miss? I missed something.
B over A.
B over A. Okay, great. Yeah, so we'll get all the terms, and we want to show this is less than or equal to twice A cubed plus B cubed plus C cubed over ABC. But
multiply by
so we can
ABC.
multiply by we can multiply by ABC, but I also want to say that you should immediately know whether or not this inequality is true. Without doing any manipulation, you should be able to tell whether or not this inequality is true. Why?
By Moorhead?
Yeah, by Moorhead, right? So what is that left-hand side is 1, 0, minus 1, yeah? Okay, so 1, 0, minus 1. We should write them always in decreasing order. And the right-hand side is what? 3, minus 1, minus 1. No, 2, minus 1, minus 1, yeah? Like this. And yeah, it measures, right? So 2 is more than 1, 2 minus 1 is equal to 1, and then the sum are both equal. Does it make sense?
Yes.
Okay, and so that you can actually, I mean, so now you can proceed in many ways. You can multiply through by ABC, but you can also find the weights, right? So what are the weights we want? Yeah, we want to take some combination of A cubed over BC, B cubed over CA, and C cubed over AB to get A over B, right? So we should maybe take
Actually, I think the equality followed from one of the problems that we have solved, I think.
it does, okay. It does, which one?
The problem 2.
Oh, it's here.
Yeah.
Okay, so you're saying if you multiply it out, it follows?
Yeah.
I see, okay. Okay, yeah, so if you multiply it out, it follows, great. Okay, and okay, so it'll follow. It can also be an exercise to figure out what the direct AMGM proof is. There should be one, right? There should be something, should be able to decide some weights here so that this is equal to A over B. But, well, okay. Okay, anyways, I'll leave it like this. Okay. Let's maybe do a couple more examples of measurization. Let's see. Yeah, okay, let's do this one. Let's do here.
But actually, I don't understand what's homogenization is exact.
What it is. Okay, yeah, so good. It's good. So, okay, do you know what I mean by homogeneous versus inhomogeneous inequality?
As I think maybe it's about the degree of the two symmetric polynomials.
Yeah, so it's about the degree, but it doesn't actually have to be polynomials. So for example, if I look at something like square root of A plus B over A squared. There's no, maybe A squared plus C, let's make it complicated. There's no, this is kind of hopelessly away from a polynomial. But I can still say this term is homogeneous with degree minus 1/2. Do you see why?
Yeah, because the numerator is 1 and the denominator is 2, and the square root is 1/2.
Yeah, exactly, right. So another way of saying this is I consider this as a function of A and B. It means that if I take and I scale them by t, it becomes t to the minus 1/2 times the function value, right? So like if I take both inputs and I scale them by a number, it becomes t to the minus 1/2 times that number. So that means it's degree minus 1/2. It's equivalent, right? Does it make sense?
Yes.
Okay. So when I look at a term like this, I know it's degree 5. When I look at a term like this, I know it's degree 0. Okay. But when I look at something like this, it doesn't have a degree, right? Because I have a degrees 1 and a degree 0. It's completely inhomogeneous. Does it make sense?
Yes. We should have like all the terms have the same degree.
Yeah, exactly, right? And it doesn't have to be a polynomial. Like you see, we can talk about degree even if it's not a polynomial. But okay, so some inequalities you have are homogeneous, all the terms are the same degree, and some are inhomogeneous. So homogenization is about if I have an inhomogeneous inequality, but if I have a condition, I can use that to create a homogeneous inequality which is equivalent.
Yes, as we did in the last inequality.
Yeah, that's what the technique is. So I do one more example. Let's look at this one, right? So let's look here. So yeah, so what is the problem? I forget already. So it's if it's 1 over a, 1 over the simple sum of 0, and I want to say, okay, a plus 1, b plus 1 is equal to more than 64. So let's assume, yeah, so we have a, b, c more than 0, 1 over a plus 1 over b plus 1 over c equals 1, and I want to show if this, then show, what do I want to say? All right, a plus 1 times b plus 1 times c plus 1 is more than 64, right? I think this is the point. Yeah. Right. Okay, so yeah, so this is kind of very hopelessly inhomogeneous. Like the right-hand side is degree 0, and this left-hand side is some mixed degree. Okay. So ideally, you want to replace it with a homogeneous inequality, right? Because almost all the inequalities in the world that exist, AM, GM, we'll learn more next week, but they all only apply, they only really work with, they only give you homogeneous results, right? So it's better if you have homogeneous inequality. So how can we produce something that's homogeneous now?
We can, I think we can expand it,
Mm-hmm. Okay.
and we will get that two of the terms are equal to 27, and we get one in the end. The ABC and the AB plus AC plus BC, we can show that each one of them is equal to 27. Or at least 27, because by AMGM, if we were to add the three terms above, which are 1 over 1 over A plus 1 over B plus 1 over C, we will get that AC plus BC plus AC is equal to ABC. However, by AMGM, we know that it should be bigger than 3 multiplied by ABC. or the square root of ABC. I don't know, we can use AMGM to show that it's bigger than 27. Then
Wait, so you want to show this exceeds 27
one
using
second, let me
AMGM?
just write it out because I haven't wrote it a bit. This is BC plus AB plus AC. Yeah.
Okay.
After this, we just use AMGM to show that AB plus BC plus AC is bigger than or equal than 3 multiplied by the cube root of A squared B squared C squared.
Okay, so AB plus AC plus BC is greater than or equal to 3 times
the cube root of A
ABC.
squared B C squared. This is just
Uh-huh.
we then
Yep,
substitute the
AMGM.
left-hand side by ABC,
Okay.
and we get that the cube root of ABC is bigger than 3. So ABC has to be bigger than 27.
I see. AC is greater than 27. Okay, great. Okay, great.
This
So
is
this one is
done.
greater than
So we get 54 and we have 1 in the M. All that's left is to show that A plus B plus C is bigger than 9, which follows by Tito's lemma since we have 1 over A plus 1 over B plus 1 over C is equal to 1.
I see. Okay, great. So okay, this is very okay.
So
It's a nice
because the
solution. So,
multiplication of them has to be bigger than 9, and since we have 1 is equal to 1, A plus B plus C has to be bigger than 9.
okay. So let me explain this. It's a very nice solution. It's not what I had in mind, but I want to explain it because it's a very good solution. So let's break it down. So okay, what do we have? We have great. So the point is first you start with the condition, and you turn the condition into this, okay? And then you have, because you can use the condition to compare ABC to itself, and you'll get ABC as at least 27. Okay. But then we're actually done, right? Because we know ABC is always the weakest term. So once ABC is at least 27, what happens then? So then, okay, because we know ABC and AP plus BC plus AC, yeah, so let's write it down. So, okay, let's move this down. So first we can call this lemma 1. Okay, so lemma 1 is that ABC exceeds 27. So, right? And then what? Now we have that, and now we have, okay, so ABC exceeds 27, then AB plus AC plus BC also exceeds 27. So we have 27, 27, 54, and 58. So what's left is 55. So what's left is 9, right? So now you want to show A plus B plus C exceeds 9.
This is done by Tito's lemma. We know that 1 over A plus 1 over B plus 1 over C multiplied by A plus B plus C. This has to be bigger than 9 since we have 3 terms and we're multiplying their sum by the sum of their reciprocals, and one of them is 1, so it just stays the same.
Okay, so one of them is T2, but we can actually just do a direct argument by AMGM, right? Which in this case is at least 3 times cube root 27, which is 9.
Oh yeah, that was right.
Yeah, so it goes to AMGM, right? So now, okay, so yeah, so this is good. And then we just get the whole thing is more than or equal to 64, right? Okay, so it's nice. It's a nice solution. Yeah, so any questions about this solution? Okay, yeah, okay. So this one, it does not use the idea of homogenization, but it's nice. So now let's, okay. So now I want to explain how do you actually solve this using homogenization. So the point is, okay, I want to create an inequality that's homogeneous by using this condition. So one thing you can do is, okay, I have degrees, everything is degree 0 except for the A, B, and the C, right? So I can multiply A, B, and C by this factor to like to make something, to make it degree 0. So I can say this whole problem, right? So the problem is actually equivalent to what? It's equivalent to, by homogenization, showing that instead of writing A, I write A times 1 over A plus 1 over B plus 1 over C plus 1. And then I multiply this cyclically, right? So I use the condition to turn A, which was degree 1, into degree 0. And now the whole thing is homogeneous. Yeah, and so what's now, now it becomes, so now it becomes 2 plus A over B plus A over C times 2 plus B over C plus B over A times 2 plus C over A plus C over B as at least 64, or it's equivalent at least. Okay. And now let me say something. Okay, yeah, so now actually this inequality, it's okay, it's symmetric on both sides, and it's degree 0 on both sides. Actually, you should know immediately that this not immediately, you should know this inequality is true by like inspecting it. So maybe someone can explain why should I know that immediately that this inequality is true? The Muirhead philosophy should tell you that this is really true. Like if you just think about it. So maybe someone can explain why.
No matter what we get, we won't get anything that's less than 0. That doesn't measure at 0, 0, 0.
Yeah. So the point is, like, let's think about, right? Both sides are degree 0. We can expand into monomials. And what kind of monomials will we get? Well, we'll get constants, which are 0, 0, 0. First of all, okay, we'll get the same. We'll get 64 on each side. We'll get constants, which are 0, 0, 0. And we'll get things that are like A over B times B over C. We'll get things like A over C, which is 1, 0, minus 1. And we'll get, actually, that's really all we'll get, I think. No, we'll also get things like A times B over C squared, I think. So we'll get things like 1, 1, minus 2. That's it, yeah? Is there anything else we can get? I can also get, yeah, I think that's it, right? That's all the kinds of terms we'll get. And all of these majorize 0, 0, 0, which is the only thing that turns up on the right-hand side. So there must be an AMGM proof to this. Does it make sense? Should I continue with what the argument is, or does it make sense?
It does make sense.
I guess I'm asking everyone else as well. Do you guys want to see the rest of this argument, or should I?
Oh, I think it's obvious.
Okay. Okay. Yeah. So I think Adham's argument is better. The reason I want to give this one is because it's kind of, you should get used to doing this kind of analysis with an inequality. Like I have a homogeneous inequality. In homogeneous inequality, I homogenize it and then I see if mirror just gives me the result. So, okay. So let's we do one more. And maybe after this, okay, we'll look at. So yeah, what is the other one I wanted to do? So it's not on here actually, so I need to. I forgot to add this one, but problem is the following. Yeah, so again, you have suppose A, B, C greater than 0, and A squared plus B squared plus C squared plus no, that is not what I want to do. That's is it what I want to do? I mean, it's yeah, okay. Okay. And like this, yeah. Then this inequality AB plus 1 over A plus B squared, cyclic sum, so it'll be 3 terms, is greater than or equal to 3, right? Let's just make sure that it's even true. Okay, let's take a moment to think about it. So what would even be the equality case here, right? So the equality case would be so we want to show this. Okay, let's just make sure we understand the equality case. So the equality case is probably when all of them are equal and this is equal to 4, right? So let's before we even solve it, let's try to see what would be the equality case. Yeah, so if you have A equals B equals C equals X, then 3x squared plus 9x squared equals 4, and 12x squared equals 4, x equals, okay, we can say x squared equals 1/3, and so we get, here we will get 1/3 plus 1 over 4/3, which is equal to 1. Okay, yeah, so the equality case we can probably predict is when x, y, and where a, b, and c are all equal and they're all square root of a third. Yeah. Okay, yeah, so it's not, okay, it's not crazy. Okay, yeah, so how should we go about solving this problem?
And we have a second.
Yeah, maybe think about it for like a little bit.